Hello viewers, it is indeed a great pleasure for me to bring to you another program in the Teleschool Senior Series. The subject today is normal probability distribution. The normal distribution is one of the most important distributions in statistics. In this program, we will show to you how to use the normal probability distribution, the normal probability table, and how to perform the calculations. Suppose that if you had the chance of measuring the mass of all adult Mauritians, say by asking them to sit on the weighing pan, then you could have calculated the average by adding all the values and then dividing this sum by the number of Mauritians. And suppose that the average that you would get is 60 kilograms. You would also know that if you were to represent the data on a histogram, majority of the values that you would get would cluster around the average value of 60 kilograms. That is, most of the Mauritians have a mass close to 60 kilograms. If you were to represent these values by means of a histogram, this is the shape that you would most probably get. Note that this distribution is nearly symmetrical. The distribution has fewer and fewer observations as the distribution moves away from the central value. That is, you would find very few adult Mauritians having a mass close to 150 kilograms. The small height of the bars indicate that there were very few Mauritians having mass close to 150 kilograms. And there were very few Mauritians having mass close to 5 kilograms. The majority were close to 60 kilograms. While a histogram is a useful way to represent these data, it will be useful for us to have a statistical distribution as a model for such variables. The distribution used is the normal distribution. The statistical model is important as it will allow us to make inferences on the variables. Consequently, if a variable follows a normal distribution, then the variable will be called a normal variable. For example, mass of a person is a continuous random variable. That is, it can take any value in a given range. In our previous example, we showed that the mass of a given Mauritian could range between 5 kilograms to 150 kilograms, and the mass of any person can take any value between 5 and 150. It can be 45.375 kilograms. Other examples of continuous random variable include time and distance. A normal probability density function has the following shape. The mean value, as I said, that in a normal probability distribution, most of the values will be clustered, will be close to the mean value of the normal variable x. The vertical axis represents the frequency density, and the curve is the normal probability curve. It has a bell shape. It is symmetrical. It is not sufficient to define a normal variable using the mean. This is because two different distributions may have the same mean value while they have different dispersions. Let's consider the case of the mass of a person. When using a normal probability distribution instead of histogram, then this is the shape of the distribution that we get. Most of the Mauritian having a mass close to 60 kilograms, represented by the large area under the curve. There were few Mauritians having mass close to 150, and few Mauritians having mass close to 5 kilograms, represented by a very small area in these regions. We can have two distributions having the same mean value. These two distributions, the distribution 1 and the distribution 2, have the same mean value, but the spread in the values are different. The spread of values in distribution 1 is smaller than the spread in the values for distribution 2. So we will say that both distribution 1 and distribution 2 have the same mean value but different dispersion. This means that to determine the shape of a normal distribution, it is not sufficient to have the mean value. We need to also mention a parameter which will indicate the dispersion. Therefore, to determine the shape of a normal distribution, we need the mean value of x and then the variance of x. Variance indicate the spread in the data. For the previous example, we will say that the variance of the first distribution is less than the variance of the second distribution. Note that in the first distribution, the spread was smaller as compared to the spread in distribution 2. So variance of distribution 1 will be smaller as compared to variance of distribution 2. We use the symbol mu to represent mean of x and the symbol sigma to the square to represent variance of x. We will summarize the normal variable as follows. If x follows a normal distribution with parameter mu and variance sigma square, then we are going to write it using the following statement. X is the normal variable. It can represent, for example, the mass of immersion. The tilde represent follows, n represent normal distribution, the mu represent the mean value of x, sigma square represent the variance of x, and the normal distribution of the variable. We will now look at the properties of the normal distribution. These properties will be very important in performing the calculations. The distribution is symmetrical about the mean value mu, which means the area on the right will be equal to the area on the left. For a normal distribution, the mean value of the normal variable is equal to the mode and the median. Mean equal to mode equal to median for a normal probability distribution. In a normal probability distribution, the normal variable ranges from minus infinity to plus infinity, and which is very important to note, total area under the normal curve is equal to 1 unit, which means that area on the right of the mean will be 0.5, area on the left would be 0.5. The total area under normal curve is 1 unit. We will now see how to use the normal probability distribution and the normal data to find probability. Suppose that we wanted to know what is the chance or the probability that if we choose a Mauritian at random, the mass would be less than 40 kilograms. Now, this is the normal probability distribution of the mass of a Mauritian. The mean value is 60 kilograms, right? We locate where we have 40 kilograms on this axis representing mass. We want the probability that the mass is less than 40 kilogram. So the area representing less than 40 kilogram is equal to the probability. The area under the normal curve is equal to the probability. Suppose that we wanted to calculate the probability that a motion chosen at random would have mass between 65 and 55, between 55 kilogram and 65 kilogram. The way to calculate this probability would be to find the area under the normal curve. First of all, we locate on the normal curve 55 and 65 kilograms. And the probability that the mass would lie between 55 and 65 is given by the area under the normal curve between the limit 55 and 65 kilogram. Now, suppose that you had to find the probability that a motion chosen at random had a mass of 85 kilogram or more. How would you be doing that? You would be, first of all, locating 85 kilogram on the axis representing the mass of a motion, and then shading the area representing 85 or more. So this is the area representing the probability that the mass of a motion chosen at random will be greater than 85 kilogram. Therefore, if you have to evaluate probabilities using a normal probability distribution model, you need to evaluate the areas. However, these areas cannot be evaluated using the standard techniques of integration, because the equation of the normal curve is quite complex. We will need to refer to statistical tables to obtain these areas. However, the statistical table that you will be using gives area under only one normal curve, the standard normal curve. And we will denote the standard normal variable by Z. So the statistical table will give us area under this normal curve. The mean value is 0. The standard normal variable will be represented by Z. The mean value of Z is 0. The variance of Z is 1 to the square. So the mean value of Z is 0. And then the variance is 1 square. We will say that the standard deviation is 1. So we have the Z-axis representing the values of Z, the mean 0. On the right-hand side, all the positive values of Z. On the left-hand side, all the negative values of Z. Note that when Z value comes close to 3, the area is very, very small. Same applies on the left-hand side when Z is close to minus 2.9. The same principle will apply if you have to calculate the area under the standard normal curve. Suppose that we have to calculate the area under the standard normal curve representing the probability Z is less than or equal to A. So the way you would do that, you would first of all locate A and then shade the area to the left, because we want area representing Z less than equal to A. This shaded region, since you're going to use it a lot, will be represented by phi of A, the symbol phi of A. So phi of A is area on the left of Z equal to A, and it represents the probability Z less than or equal to A. As we said earlier, the total area under a normal curve is 1, which means this unshaded area, which will represent probability Z is greater or equal to A, will be given by 1 minus this area, which is 1 minus phi of A. So it is very important for you to remember, probability Z less than or equal to A is phi of A. Probability Z greater or equal to A is 1 minus phi of A. Note that since the normal probability distribution is a continuous probability distribution, there will be no difference in the probability of Z less than A and Z less than or equal to A. Therefore, probability Z less than A will be equal to probability Z less than or equal to A. It will be equal to phi A. Remember, less than phi. Probability Z greater than A will be equal to probability Z greater or equal to A, and equal to 1 minus phi, greater than 1 minus phi. Probability of Z lying between A and B will be equal to phi of B minus phi of A. Probability Z lying between A and B is equal to phi of B minus phi of A. Let's take a look at the normal probability distribution table, which you'll be using to calculate the area. So this is the normal probability distribution table that you will be using in order to calculate the area. Definitely, we'll show to you how to calculate the areas and how to read from this statistical table. Let's see the region in the statistical table. It is divided into 3 regions. The first column here contains the unit and the first decimal point in the value of Z. So all the values in this column are values of Z. The values on the top between 0 and 9 are the second decimal points in the value of Z. And here, these digits represent the third decimal place in the value of Z. If we compare it with the Z-axis, you will find that only the positive Z-axis is represented in this normal table, in the first column and the top row. So the positive Z-axis is represented in the first column and the top row. If we wanted to locate 0.2, so 0.2 on the Z-axis and 0.2 on the table. 0.21, 0.2, and the second decimal place 1. We will take some examples to show to you how to evaluate phi and the area under the standard normal curve. Let us find phi of 0.42. We have to find phi of 0.42. So this means that in the value of Z, we have 0 unit, first decimal point 4, second one 2. So we need to locate, first of all, 0.4. 0.4, and then the second decimal place is 2. And we read the value of phi. So this is the value of phi. Phi of 0.42 is 0.6628. Phi of 0.42 is 0.6628. Let's take another example which will illustrate how to use all the values given in the table. Suppose that we have to find phi of 0.425. It means that z, the value of z here is 0.425. So we need to locate, first of all, the value of z. 0.4, 2, and then 5, the third decimal place, 5. The value here is 0.6628, which we write here. And in the same row, the value here is 18. It is not 18 units. In fact, it represents 0.0018. So we write 18 here because in fact it represents 0.0018, which we add to the last dp in order to obtain 0.6646. So here the value of z was 0.425. In order to find the value of phi of 0.425, first of all we located 0.4 in the first column because the unit was 0 and the first decimal place was 4 in value of z. The second decimal place is 2, whereas the third one is 5. So we read this value, 0.6628, and then continuing in the same row until we reach the value 5, representing the third dp in value of z. We take this value and add it to the last digit in the value of phi obtained in order to obtain 0.6646. Remember that phi represented the probabilities that z is less than equal to 0.425. So probability that z is less than or equal to 0.425 is phi of 0.425, which is equal to 0.6646. As we have said that the negative values of z are not available on the statistical table, which means that we'll have to find another formula in order to calculate phi of negative values. So let us see. If we have to find phi of minus a, then this represents the area to the left of minus a, phi of minus a. And we said that the normal curve is symmetrical. The normal curve is symmetrical, which means that phi of minus a will be equal to phi of a by phi of minus a will be equal to the area on the right of z equal to a. These two areas will be equal by symmetry, which means phi of minus a must be equal to 1 minus phi of a. So phi of minus a is equal to 1 minus phi of a. So this is the formula that we will be using in order to evaluate phi of negative values of z. So if we had to calculate probability that z is less than or equal to minus 0.425, then this would be equal to phi of 0.425. Phi of minus 0.425, which will be equal to phi of a negative number is 1 minus phi of the positive value. So phi of minus 0.425 is 1 minus phi. Remember, we had less than, so it was phi of minus 0.425. But the table doesn't allow us to have negative values of z, so we use the formula to obtain 1 minus phi of 0.425, which we had already calculated, which gives us 0.3354. So probability that z is less than or equal to minus 0.425 is 0.3354. In the same way, if values of phi are given and you are required to find the value of z, you will need to find or evaluate phi inverse. Let's see how to find phi inverse. Suppose that probability z less than or equal to a is phi of a, and the value of phi is equal to b. Remember, z is less than a, it is equal to phi. If it was greater than, it would have been 1 minus phi. Z less than or equal to a is equal to phi is equal to b. This implies that a will be equal to phi inverse of b. How to evaluate phi inverse of b? Let's take an example. Suppose that you are told phi of a is 0.9699. Phi of a is 0.9699. Find the value of a. So a would be phi inverse 0.9699. In order to do that, we must locate the value of phi, which is 0.9699 first, and then read the value of z in the first column and the top row. It is 1.88. So phi inverse of 0.9699 is 1.88. Not always you will be lucky to locate the value of phi exactly in the statistical table. Very often, the values that you would require will not be found in the exact form in the table. So let's take an example to see how to find phi inverse. Probability z less than or equal to a is equal to phi a is equal to 0.95. A is equal to, therefore, phi inverse 0.95. So let's try to locate phi inverse of 0.95, that is 0.95. You will find that 0.9500 does not exist in the statistical table. So in this case, we take a value which is closest to 0.95 but smaller. Closest but smaller. The value that you will find in the normal table, which is closest and smaller, is 0.9495. Then, in this region, we find the value that we need to add to this smaller but closest value in order to obtain the value that we wanted. So we have 0.9495. We need to add 5 in order to obtain 0.9500. So we have located that 5. So the value of z in this case would be 1.64, and this 5 corresponds to the 5, the third dp in value of z. So we would say that phi inverse of 0.95 is 1.645. Phi inverse of 0.9500 is 1.645. Again, since the table has only positive values of z, in order to find phi inverse of values which are less than 0.5, we need a different formula. Let's see. If you consider this normal curve and take a value on the left of the mean, this area would be less than 0.5 because the total area is 1 unit, the area to the left will be 0.5, and any area that we'll take would be less than 0.5. So if you have to find phi inverse of A, where A is less than 0.5, then phi inverse of A would be given by minus phi inverse 1 minus A. Suppose that we have probability Z less than or equal to A is equal to 0.2500. Since we have probability Z less than A, it becomes phi of A is equal to 0.2500. Therefore, A is equal to phi inverse of 0.2500. Note that 0.25 is in this range between 0 and 0.5, that is less than 0.5, which means that we need to use the above formula. So it becomes minus phi inverse 1 minus 0.2500, which is minus phi inverse 0.7500. This we can find from the statistical table in order to obtain minus 0.674. You will agree with me that all natural variables are different from the standard normal variable because they don't have a mean value of 0 and standard deviation of 1. How can we use the standard normal table to find probabilities of such variable? We must use the process of standardization. In fact, any normal distribution can be mapped onto the standard normal distribution. So if X follows a normal distribution with mean mu and variance sigma square, the sigma is the standard deviation, sigma square the variance, we need to standardize it, that is map it on the standard normal curve, the normal variable Z. Transform X onto Z by the following transformation. Z is equal to the normal variable minus the mean value of this normal variable divided by the standard deviation. Sigma square is the variance, sigma is the standard deviation. By using this transformation, if we had to calculate probability X is less than or equal to A, then we could simply transform it by using the following transformation. Z less than or equal to A minus mu over sigma. And since we have Z less than, it becomes phi. We have replaced X by Z, and the right hand side we have transformed it, transform X onto Z. Similarly, if you have X greater or equal to A, it becomes probability Z greater or equal to A minus mu over sigma. Since we have greater than, it becomes 1 minus phi. So we had probability on normal distribution for which the mean was not 0, the variance was not 1, but we transformed them in the form of the normal, standard normal variable, and then we wrote that expression in terms of phi, and this phi can be found using the statistical table. So any probability on a variable which is not the standard one must be transformed using these two equations and then written in terms of phi, which need to be evaluated using the statistical table. We'll take an example. An industrial process produces a large number of items whose weights are normally distributed with mean 18.5 kilogram and standard deviation 1.5 kilogram. What is the probability that an item chosen at random weighs more than 21.5 kilogram? The first question we ask ourselves, what is following a normal probability distribution, the mass of an item? it is advisable to use the letter x to represent that normal variable. So x follows a normal distribution with mean 18.5 and standard deviation was 1.5, so the variance would be 1.5 to the square. We wanted to have the probability that the mass is more than 21.5, more than 21.5. That is, the mass x is more than 21.5. So we need to transform it, map it onto the standard normal variable. So mapping it would result in 21.5 minus the mean, minus 18.5, divided by the standard deviation, which is 1.5. So 21.5 minus 18.5 divided by 1.5 gives us 2. So we have to calculate probability z is greater than 2. Greater than, so it becomes 1 minus phi. Greater than 2, 1 minus phi of 2. Phi of 2 can be found from the statistical table, which gives us 0.0227. So viewers, this brings us to the end of today's program. In this program, we have seen that the normal probability distribution is a very important distribution, and that we can calculate the probabilities using the normal model, using a normal statistical table. Thank you for your attention. Until next time, it's goodbye from us.